Hi, so welcome back to the GPIO related mm, GPIO related RTOS section where we will be downloading the actual code for a GPIO initialization and hello world example. So what I wanted to just tell you in this particular lab is that I will show you how to create your own workspace in Code Composer Studio, and in your own workspace you will be able to create or rather not a create, I would say import a simple link, but I will also give you an overview of how to install this simple link into your CCS. So in case if you have just downloaded your CCS and you are new to this particular IDE, then just like you can have a overview of something which is called the Resource Explorer. The Resource Explorer basically gives you a one, you can say a one in place for all the resources that TI has for you. So when you just connect your launchpad, the launchpad is already connected. I have already connected the launchpad to my laptop, and so in the Resource Explorer you will basically have these divisions, these particular sections. So in the software section, you just have to look in for the kind of package you are heading, you are wanting to install. Like for example, you can see that we have MSP430 wire, we have C2000 ware, and also the TI stack and RTOS, and also T for the TM4C ARM Cortex M4F family SDK. So what we would be interested is like the simple link plugins. So once you know that which launchpad and which target you are using, so we are using CC32XX target. So for CC32XX, this is the particular I have just highlighted it, and this is the particular one that we will be requiring. So in case if you don't have this green tick beside it, which means that like it is installed locally, so what you have to do is you just click on the three dots, and it will give you an install option over here. It is showing me uninstall because it is already existing in my system. And always remember that CCS, which you have already installed, the default directory is C drive, and inside C drive there's a folder called TI. So C/TI is the location by default for the CCS or Code Composer Studio. Now this simple link, whatever folder or whatever simple link SDK you will be acquiring from Resource Explorer, will by default go inside this C/TI. So it is also recommended that you follow that particular path, so that all the resources and the include options which are there given in the CCS various linking path libraries, they work properly. So after installing this, once your this simple link is installed, this you can just expand this simple link, and you can see that there are various folders. One is the simple link academy. This is something that is very important and very interesting. Simple link academy is basically a guidance which is provided from Texas Instruments side, and it contains sample examples on how to initialize and run this particular target with various kind of peripherals. So simple link academy is the tool for a beginner to learn this particular platform. There are also some examples, like for example, it will first ask you like which type of the development board do you have. Since we have a CC3220SF launchpad, I will just click on that, and here you can see that there are different type of examples, like some demonstrations, some network services demonstrations, or examples, some TI driver examples, TI utility examples, and some kernel, it's TI RTOS kernel examples. So for those who are quite familiar to a real-time OS, I would say that you can go through the TI RTOS kernel examples. Inside the TI RTOS kernel examples, there are some really good sample programs that has been given. For example, the mailbox, how you can use a mailbox to send data from one process to another process, how to do a memory management, how to do the mutex for for any kind of resource management, if you want to block the mutex, how to manage with a semaphore, and how to synchronize threads. So all these things have been beautifully explained in the mutex example. Stair step stop mode, this is another wonderful example that will help you understand the system analyzation load, for in case if you're running, and suppose if you're running the if your core is running a particular application, and while running it and pausing it, you can just do an analysis. Software interrupts is another important thing for any RTOS. So if you are implementing, well, if not, you will be implementing, rather I would say, you will be implementing any kind of software interrupt, and this particular example will show you how you can implement a software interrupt. So the kernel, these are basically all kernel related examples, I would say. Big time is something that gives you the total time, that wherein you can have a, it's like a real-time clock application, so you can also have a look at this. And also the error handling, as we know that for those who are new to RTOS, let me tell you that in RTOS, whenever we create any particular say thread, we do have a particular structure, a data structure, wherein the error is handled or the error is handed over. That is, suppose if you want to create any particular thread and the thread could not be created due to some error, so the error block data structure will basically hold the error which your RTOS has encountered while trying to create your thread. So from that error analysis, you can use to catch. I mean, I'm sure most of you are quite aware of catching and raising errors. So you will be able to analyze that what are the sources of these errors, how they have been caused, the failures, and you can actually print them on the UART. And also UART logging is there. This is another important feature. UART logging is basically like there is some kind of you create an handle. I mean, I'm sure that like when I'm going through these kind of courses, I presume that you are like to some extent familiar to the RTOS overall structure. So in RTOS, usually whenever we try to show some data through the UART, so we do not use the normal printf, we have a system printf or display handle. So we create a handle for a particular UART initialization, and after getting the handle, we pass on the handle, and through that handle we will be passing on data with whatever we want to display on the UART console. So this particular application shows you how to use the UART driver and how to create that handle and pass on some data to show on the UART. So in one more thing, in all of these examples you can see how to how to use the ROV, that is a runtime overview, and logic analyzer, and you can actually see that how much time has been consumed by one particular task and how much time was given to the idle, and if there was some higher priority task, if you had, I mean, if you had implemented threads which were in in separate in separate priorities, which has preempted each other. So you can actually have a graphical overview of how much time has been given and to which thread, and for that we need to enable something which is called the logging. So I don't want to get into much details of the RTOS right now, because that will be a total different scenario. Maybe I will make a separate video tutorial on TIRTOS, but or maybe you can also get it online. There are much good TIRTOS tutorials available from TI. So that is something that you can look into yourself. And let me now see the TI drivers. The TI drivers folder has some beautiful examples. You have this ADC single channel example. The ADC single channel example will show you how to acquire data from from one of the channels which are given for the user. That is, I mean, there are basically, I've been you can see my ADC particular section of the video, and I have also told you that there are four channels which can be used by the user. There is channel 0, channel 2, channel 4, and channel 6. So these 4 channels are user application channels, and in this particular example, there's only one channel has been taken, and you configure the channel for multiple scannings, and whatever data you get in the single channel, you print it to the UART. So this is just a hands-on, you can say a jump start on how to configure the ADC, and how to create a thread, and how to make that ADC access the UART, and through the UART you can print the display data. Button LED is another example, which in which we use the GPIO, because here what we are basically will be doing is like some button will be created, I would say rather some button instances would be created, or rather button objects will be created, and their handle will be passed over, and using that handle we can actually detect that what condition the button has come into, and we will also be creating LED handles for each. If we use multiple LED, we can do that. If we want to use single LED, we can also use that. So for the LED also, we have to use the LED drivers, and we have to create LED handle, and according to the button condition we process the LED handle. So you can just go through all these examples. They are very nice examples. FAT file system reading, if you are using FAT file system for SD card, this particular example will be very helpful for you to jumpstart a project. If you are doing some I2C computation, then you can follow this particular example. Usually what they are doing in this particular case is, I told you that CC3220SF do have a temperature sensor on board, and that temperature sensor is an I2C sensor. So what they are doing is they are initializing an I2C object, and through that I2C handle they are acquiring data from the temperature, and that temperature is being printed. So this is a very nice example on how you can use the I2C peripheral for your own purpose. The PWM is another wonderful example. It creates a PWM pulse for the onboard LEDs, and you can actually control the onboard LEDs with the PWM duty cycle. So this is a good example if you would be using PWM in your project. Also, if you are interested in Spi Master, then this is the example for you. For the Spi Master, as we know that there are 2 Spi channels. One is dedicated for the user flash, and the other is for the SPI slave. So if your CC3220SF is a Spi Master, then this is the example that you would be requiring. And if in case you want to communicate with another Spi Master where CC3220 is a SPI slave, then this particular example will help you make a jump start. So these are the SPI related examples. There is also a timer related examples, wherein according to the timer, periodically the timer will be expiring, and it will be generating an event, and there will be an LED handle that will be created, and through that LED handle we can control the toggling of an LED, and the timer element which will be created, we can create it in one of the 2 ways in RTOS. As we know that through the module we can create a static timer, or we can also create a dynamic timer object. So whichever process you follow, you just have to declare that the timer will be running not in a one-step mode, but it will be a continuous running timer, and it will be generating some fixed delays, and according to that delays we will be toggling the LED. So this timer LED is a beautiful example if you want to understand how the timer functionality is done, and also the LED. Okay, now UART echo is a very simple example, like whatever data you send to the Uart driver, it is echoed back to you. And watchdog is also another important example, wherein you will be using the watchdog. So these are in the TI drivers. In the network services, this is something that is very important. If we plan to use any kind of TCP applications, the TCP echo will help you understand how TCP applications can be done. And for UDP, you can use the UDP echo. So this is a beautiful application. I think you can wait for my TCP and UDP sections, wherein I will be describing these in detail. Now coming to the demo section. In the demo section, it's basically like some very basic functionalities which is very important has been given as an example. For like, if we consider the out of the box, this particular example, whenever you buy a new launch pad, you will have an out of the box example. Now I don't want to go into the depth of the out of the box example because it is there, a lot information is there on the online as well as YouTube. So whenever you buy a new launchpad, you connect your laptop to your Wi-Fi through the simple link Wi-Fi network, and you can actually connect to the web server that is already there inside it, and you can control the LEDs, and even if you can see that what are the values that are being acquired from the accelerometer which is there on board. Now for the people out there who are working on MQTT client and MQTT client server, these examples are really interesting because if you are like trying to connect the launchpad as an MQTT client, then this example will give you a very good basic jump start to your project outline, and you can customize it according to your requirements. Similarly, if you also need to forward the request to another server, another MQTT broker server, then you need to have, I think, more than one launchpad for this example, in which one will be acting as the broker that will be forwarding the requests or the subscriptions to the internet or to the remote broker, and the other one will be acting like a local client. So this is a nice one if you want to explore MQTT. If you want to explore REST APIs, this HTTP GET is the example for you. HTTP GET will just will give you an overview of how to set up an HTTP GET request from your server, that is from your HTTP server that is inbuilt. I can just show you here. This is the host name that is given on the right, and here is, as we know that there in REST API there is a request URI which is a part of the valid URL, so that you can modify yourself, and it will constantly be in sync with the server, and whatever changes you make will be reflected. And you can also use your own host name, like for example, like I did it for my own domain website that I have. So you can, if you have such a setup where you are already running some kind of REST API control, then you can very well test this particular application right with your own domain. Okay, so now I will also go to one of the examples which is called portable. Portable is a very important example because whenever you want to start any kind of multi-threaded application that uses not only a single driver but multiple drivers, you should directly start from this portable, because the portable project or the portable example basically initializes all the required kind of kernels, device drivers, and it has all the compiler settings properly, and here you can just add on your module, and from there you can start your project. So it's like you have everything in place. There are APIs which are POSIX compatible, so you don't have to worry about portability, since POSIX compatible APIs can run under multiple targets. So this is the particular example from where you need to build your own example. Okay, so I think that was all about the basic example demos. Two more important demos there. One is the provisioning. Provisioning is something like whenever you provision a device on the wireless network, you connect it to the wireless network. So provisioning is something that I will be doing when I will be explaining the Wi-Fi network part of it. So whenever you want to connect your device to a network, this provisioning has to be done. And there is one more important, is the power measurement. So as we know that this device do support multiple kind of low power modes. So in this particular example, we can measure how much power the core is actually consuming, and we can actually play around with this particular example to see how much power is being measured, and how the power management is handled inside. using the current measurement tool. So this is another very important example for you guys who want to make applications which will be running from battery, because battery running applications need to conserve power, and that is very important. Okay, so let me just now close all this. I mean, otherwise it will get very boring for you. Let me just close all this. What I will do is I will be creating a new workspace. So just remember that whenever you want to create a new workspace, you just go to file and then switch workspace and then go to other. Okay, so in other you go to browse. In browse, whatever is your disk location where you want to store your workspace, just create a new folder. And suppose I give the name as Sandeep Projects or Sandeep Workspace. You can use any name you want, right? So just select the folder, just use this button, select folder. There you go. And you know what I will do is I will create it directly under D drive. That will be very helpful. Okay, so here I have created under D drive, and I just say select folder, and then I say launch. So when it will launch, it will take some time, because I am just creating a new workspace wherein all the settings will be copied. CCS has some very good standard settings for its compiler and other linker files, so it will take some time. Okay, so this is the kind of thing that you will be seeing if you are creating absolutely a new workspace for yourself. So here we know that this left part is called the Project Explorer. So what we will do, we open the Resource Explorer over here, and inside the Resource Explorer, as I said, we open the software. In the software, let me tell you one thing, guys. In case if you feel any problem is there when you are installing the SimpleLink SDK, you can just drop me an email at turjashu@turjashusworld.in. Okay, I will just write it. So this is the email ID. You can also send me a WhatsApp, and this is the number. So either you can send me a mail directly, or you can just give me a WhatsApp. So because there are sometime there are cases that it just your SimpleLink gets stuck, your SDK doesn't get downloaded properly. So these are some small troubles that keep on happening. So in case if you feel so, you can just contact me. I will try to resolve it. Definitely I will try my best. And if in case if you feel that I'm getting too late with it, there is one good thing, that TI has their own forum. It's called e2e.ti.com. So TI really has a very good people, a set of very good people who reply very quickly to your questions. So you can just go to e2e.ti.com and search the particular community. For example, if you are working with CC3220SF, you have to go to the wireless community, and over there you can post your query, and they will try to resolve it as soon as possible. Okay, so let's get started. So what we will do is, like, we have studied the basics of GPIO, and so what I will do, I will just pull in an example from here. So we have selected the button LED example. So what we will do is, we will just read the basics of this particular project first. So that will help us to understand what we are actually wanting to do. Here, see, what are the files that are given to you. you have a folder that says FreeRTOS, you have a folder that says TRTOS. So those who want to develop the application using FreeRTOS can select this folder. Those who want to do it using TRTOS can select this folder. Now basically this is a sample application. This is basically a sample application to handle buttons and LEDs via the buttons and LED drivers. So as I told you that there will be, buttons in RTOS are treated as button objects. So we will be creating some button objects, and we also have onboard LEDs. We have 3 onboard LEDs, so we can create some LED objects using the LED drivers. And after that, it will be only a simple task to create the detection of the condition of the buttons, and accordingly just pass on to the LED handle, and do whatever we want to do with LEDs. So we can see here, you can come a little bit down. You can, for time being, you can just ignore whatever they are saying over here. If you come down here, you see config button 0. So basically we have 2 buttons on the board, right? So one is config button 0, one is config button 1. We have given these names. Okay, I will show you where these names are given in the xgconf editor, but the main point is that you have to select a name. So we, as a standard convention, take this name as config button 0 and config button 1. Now button instance used for register button presses, and this is another button instance which is used for another register button presses. So you can use any name you want, but I just want to go with the convention of config button 0, config button 1. And also the same for LEDs. You can see LED config LED 0, config LED 1, config LED 2. Now what I want you to see is that for the 2 buttons, we have selected 2 LEDs. You can see that LED 0 is an LED instance which is used to control the onboard LED using GPIO. So you will be controlling one of the 3 LEDs with button 0, and that will be called as LED 0. Now it doesn't matter which LED to which GPIO pin it is connected. That is up to you to select. Another LED will be used to be interfaced with another button. Okay, and the third LED, most probably, which is the LED in between. If you have the same board as I have, then it's a yellow colored LED. Then the yellow colored LED will be, it will be just used as a pulsating control using a PWM. So we all know how to just glow an LED, or increase the brightness or decrease the brightness of an LED, or pulsate an LED using using PWM duty cycle. So that is what done for the third LED. Now for all those who have messed up with the jumper settings, there is one particular file which is called board.html that will be there. I will show you where it is. In that particular file you will see that which jumper needs to be placed where for this example to work. And apart from that, you will have a Uart connection, UART, wherein the settings are these. So if you are using putty, or you are using any other any other software for capturing the UART data, it's up to you. You just give all these settings, and once you connect your device to the PC, you can just go to this PC, or rather I would say the device manager. Okay, so in the device manager, if you expand the ports, you will see that 2 XTS110 ports are created. Okay, so we will be using this particular port, which is the user port and not the data port. Okay, so that is COM3. Okay, so now what I will do is I will first open my hyperterminal, or HTerm, and I will select COM3. I will give the baud rate, and I will just say connect. Okay, so there's some example that is running. That's why I'm having some data. I will, for time being, I will minimize it, and so that is all that we will be learning in this particular example, nothing more. So what we do is, after selecting this, we go to TI-RTOS folder, because we are using TI-RTOS. So when you click on the TI-RTOS folder, you will be asked for what type of compiler you are using. So if you're using IAR, you can go for this. If you're using a GCC compiler separately, independently, you can go for this, but I am using CCS IDE version 10, so I will go for CCS. Inside CCS, once you take the mouse over here, there will be 3 dots, so you can just Once you click on the dot, this option will come, import to CCSIDE, and it will ask you that what target are you using. Now we are using CC3220SF target, and we will just say apply, and the project is getting created. Okay, so here we see something interesting happening. If we see on the left, you can see that there are two projects. One that says button LED launch XL TI RTOS, and the other that says TI RTOS builds CC3220SF. Now let me tell you, to those who are new to RTOS, whenever you are using an RTOS, you need a kernel. So the till now what you can think is like the TI RTOS builds is basically the kernel, and that contains all the kernel files and the basic files that TI RTOS has requires for its own functioning. So this will be a common project that will be shared by all the TI RTOS applications that you design. And the second project is the button LED that we have imported. So now let me expand the button LED and the TI RTOS. So in both of them you can see that you have a lot of files. So if we just see inside the TI RTOS, you don't have any such file that you can open and see. There is no C file. So as I said, it has all the related includes and all the related configurations that the TI RTOS kernel needs to function. But what we main need to see is this particular file. So main TI RTOS.c, this is the main file from where our project will start functioning. I will be very basic. I won't go into much criticalities of the RTOS functioning, because that will make this particular tutorial not oriented towards what I want to do. I want to show you how to configure the GPIO and how to access it. Like I don't want to go into the in-depth part of like what is sysbios.h and driver/board.h. all these things, these are TI RTOS related points, and I will definitely try to create a separate video for that. Okay, so just remember one thing, that this thread stack size is something that is very important, because whenever you declare any particular thread, or for example any particular task, what happens is you have to assign some amount of stack to it. Like for example, here we are creating a thread which is called main thread. You can see it over here. Okay, we are creating main thread. So for this main thread to operate, you must allocate some stack size, because whenever a thread or a task is created, like it needs some memory space in the RAM where it will keep its own its own variables, its own properties, its own you can say register statuses. So for that we have to allocate a separate stack to this particular thread. So this is the amount of memory that we allocate. It is 1024, and so this is something that is very important to note. Okay, after that you see that inside the main function we are basically creating a thread object of the structure, that is pthread underscore t. So all those of you who have already worked on POSIX, they know that what these kind of structures are, and those who are new, for them I would tell you that whenever you need to create a thread, there are certain structures that needs to be, there are certain data structures that needs to be followed, and objects created in that particular structure or variables created with that particular structure needs to be attached to the thread which you want to create, because these are the memory areas. To simply put, these are the memory areas where all your thread related data will be stored. Okay, so pthread underscore t is actually the thread that you want to create. This attrs is nothing but a variable having the structure of pthread attributes. So whenever you have a thread creation, there are some important points like the priority, how much stack you want to give to it, whether it will be created in a detached state or in a joinable state. So in a detached state, it's like usually when a thread is created in a detached state, after the completion of the thread, it will release and relax the memory that was occupied to it. But in case of a joinable thread, it is not returned and not relaxed. So for that you can just have a look on you can just Google for these kind of things, like what is a detached thread and what is a joinable thread. So these are the attributes that needs to be mentioned. So we must have some memory architecture or memory structure or memory area allocated where we can save these properties. So for that particular reason we create this variable. Now after that we have another struct that is like, which is called schet param. So basically whenever we are creating a structured a structured thread or a structured data type for thread, you have a schedule state, that is either it is in a detached state or it is in a joinable thread. And then you also have the priority for that particular thread. You might be having, rather I would say, you will be having multiple threads which will be created and they will be running at multiple priorities. So for that we have to create this particular variable in this structure. And there is one more integer, that is ret_c. Ret_c is nothing but it just returns the value whenever we call an POSIX API. So the first, after all these thread properties have been created, what we do is we do a board init. So I will just say that this board initialization is nothing but the initialization of the TI drivers for all the peripherals that is given inside the CC3220SF. So you don't have to worry, you don't have to bother about any kind of initialization of the clock, of the memory, of the peripherals. They are all taken care inside this particular function call. So you have to do this board init at the beginning if you want to initialize your particular board. If you are not using this particular launchpad, if you're using your own target, then you have to build your own board init function. Or what you can do is you can just copy or rather keep the design same. In that case you can use this board init function. So it is a very basic level of initialization of TI drivers for your launchpad board. And after that what I do is I initialize the ATTRS. So that attributes variable which I have created, I give and allocate a memory for that. After that you can see that I have given the priority level to the thread as 1. So that's like the priority of the thread. Okay, now there are certain parameters that I pass. For example, that I have passed this parameter that this thread will be a detached thread, which means that it will not be a joinable thread. It will return all the resource that will be allocated to it once it gets finished. And I also pass the thread stack size, because I have to tell the thread how much stack this particular thread will be using. So if everything goes well, you see that ret_c is taking the reply from all these APIs, all these POSIX APIs, and these POSIX APIs are again included in the POSIX header file. So you have to look into the fact that this POSIX header file is included. If you're importing this example, it will come by default, but in case if it doesn't, just write pthread.h. It will include the POSIX APIs. So if it is created successfully, fine, otherwise your processor will come into the halt mode. Okay, now once all these variables has been initialized, and basically what we do is we assign some memory to these variables, these data structures. Once that is done, we can go ahead with the creation of the thread. Now in the creation of the thread, pthread create takes 3 parameters. One is the name of the thread, which we have given as main thread, which is the third parameter. The other is the pthread, that is we are trying to create a new thread, so that is where we pass the data structure for thread itself. And one more important thing is we pass the attributes, that is the variable which we created for the attributes. We pass the address of that particular variable. I mean, because we have assigned we have allocated some memory to the ATTRS variable, so we pass that memory address wherein pthread underscore create will try to fill in the attributes. So the last parameter, or the fourth parameter, is like if you want to pass some kind of argument to your thread, but right now we are not doing that, so we can keep it as null. And main thread is the name of the thread which will be running in my entire application. Okay, so the main thread is the thread which is actually taking care of reading the buttons and blinking the LEDs. So after this thread has been created, we again take the reply or whatever is the return from the pthread underscore create into red C. So once red C is okay, I mean if it says that okay fine, I have created the thread properly, what it will do, it will immediately go to the next thing which is called the biostart. So when the biostart is called, by default like the threads which has been created, they will be scheduled. Okay, so for this you have to read one particular document. I will show it to you. uh, yeah, so if you need to read all these kind of details about how the system, how the TI-RTOS kernel functions, how it works with the POSIX, how we can create without using POSIX, what is the like the timing services, what are the instrumentations that are available. So all these details are given in this literature, so you can take a note of this particular literature number. It is SPRUEX3U, SPRX SPRUEX3U, and you can just go to Google and download this particular document, and you need to go through it very rigorously. Otherwise, if you are already working on RTOS, then you don't need this particular thing. So the biostart will basically schedule the threads that has been created. Since we have created only one thread, so it will start running. Now what we will do, whenever you want to go to this particular thread, wherever it is defined, you just hold down the control button. I will again say, you just hold down the control button, take your mouse and left click on the name main thread. You can see that an underline is coming, right? I will again say, hold down the control button, take your mouse to the name main thread and just give a left click. You will see a wonderful thing. An interesting thing has happened. What has happened? I have moved out of my main tirtos.c. I have come to my own source code, which is buttonled.c. I mean, rather, by the word my own, I mean that the application that we are interested in. So here you can see, like this is my entire main thread. Okay, so I will just go through very basic because it's a very big one. It's a very it's a very elongated one. If I go into details, then it'll take a hell lot of time, and it'll maybe it'll get weird. So you can just go through like what are the header files that are included. Gpio.h is required for Gpio functionality. If you remember, I said that there are many registers that needs to be configured for GPIO functionality. Exactly those things are done in gpio.h. We need display.h in order to show the UART. Okay, we need a ring buffer. A ring buffer is something wherein, suppose if you are pressing the buttons, excuse me, if we are pressing the buttons, then the events of the button press will be placed into the ring buffer, and whenever the LED handle is ready to function, it will automatically take out the command from the ring buffer, and the buffer will be cleared. So ring buffer is kind of, you can say, a linked list kind of a thing, like a circular linked list kind of a thing, which just stores your command. Okay, led.h is required for LED functioning, and button.h is required for creating the buttons. So you can see that these are all just simple parameters like blink count, how much it will be, the fast blink count, how much it will be, slow blink count, how much it will be, delay. Okay, so all these things you can just go through yourself. I'm just I mean, it can be an exercise for you. There's nothing much important given in it. Okay, so next we come to the structure button stats. In button stats, we have it is basically a structure that gives you all the conditions that is possible. So one can be you've just pressed the button and held it. Other is you have just clicked it once. One condition is you've just released the button. So these are, I would say, these are instead use cases or exact state machine use cases. So that is how you can relate it. Okay, so it can be a long press, it can be a long click, it can be a double click, and its last pressed duration, that is how much time you have spent when you have held the button. So that is a structure that we follow for the button statistics. After that, we have given some name to the button handle. So whenever we are creating a button handle, we know how many button count it is. Here we have 2 buttons, so you can see the macro expansion is 2. So we have an array with this particular structure. After that, we have a LED handle, and then there is a display handle. So like this, we create a handle for each and every object, okay, and also for the ring buffer. So after this, we will straight go to main thread. So now you understand what type of handles are there. You can just go through this particular code and let me know if you don't understand something. I will definitely try to clear it up. So in the main thread, what we do is basically we again declare button params. If you see that we have already I just explained how many kind of button events can be there, or rather state machines conditions can be there, but this button params is inside button.h. So in button params you have like debounce duration, how much debounce you need to give, okay, then long press duration, how much long press duration you need to give. So these are parameters that will be evident for each and every button press, or rather for each and every button. So for that we have to create a variable with this particular structure. The same goes for LED, and after creating these two variables we have to do a Gpio init. So this Gpio init is what I was telling you. This Gpio init will create the most important thing, which is it will initialize the clock gating, it will initialize the GPIO registers, and it will do everything that needs to be done properly in the GPIO registers which I had shown. Okay, we also need to do a button init. Button init will create, it will create instances properly so that the button handle is generated. Similarly for the LED init, ring buff construct will basically create a ring buffer wherein your events will be inserted one by one. And then what we do is we create a display open. Now display open is a function which will basically return a handle to the UART you have created. So let me explain what it is. So you want to see whatever button you press, you want to see it in a UART. So in RTOS, how it is handled, whenever you press the button, an event will be generated, and that particular event will be passed on to the UART driver. Now when you access the UART driver, you basically create an UART driver object, okay, and that particular object will have a handle. A handle can be considered as an argument. If I mean, that is how I imagine it, is like an argument. So once you have the handle, you have the access to that particular object, and once you have access to that particular display object, which is nothing but a UART driver, whatever data you send to the handle using the display print function will be displayed in UART. So once this handle is created properly, you see here display underscore print 0 is a function wherein you again pass this particular handle, right, and you just write whatever you want to show in your UART. So this display print 0 function, the main utility of this display underscore print 0 function is to show this particular text on the UART, right? So after that what we do is we do a button params in it. So we had a lot of parameters for the button. For that we have to we have already created the button params over here, and we need to pass the address of the memory area which has been allocated to this particular structure, and that is exactly done over here. And once you pass the button params initialization, the address of the button param structure, the next thing that you need to do is you have to open the particular handle. So basically if you consider this particular function call, what we are doing is we have created a button handle, and we have also passed in the memory area which is related to the button parameters. So whatever happens or event happens in the buttons, that needs to be stored in the button params memory area. So for that we need to first open the button, and when we open the button, this button open function will actually try to access the button condition or the button handle, and there we have passed on the number of the button. If you remember, we had created. So let me show you one particular file in this respect. Exactly right now is, if you see left, you have a file called buttonled.sysconfig. You just open that file, although it's a part of the RTOS, but I will just say something basic. Here you can see that all the peripherals are listed. So if you go to GPIO, you see that we have added with this plus button. So there are four GPIO inputs that are considered, out of which two are LED0, LED1, and two are GPIO 0, config GPIO 0, config GPIO 1. So config GPIO 0 is nothing but a button, and here if you explore, you will see that you can actually tell that whether it will be a rising edge button or a falling edge button. And right here you can also see that which pin or port number it is connected to. Okay, so here you select it as launchpad user button SW2. For GPIO 1 we select SW3. Okay, here you can see the pin number. Okay, and for LED 0, config underscore LED0 GPIO, you can also configure it. We configure it in the mode of output, right? And below, if we come, we will see that it's in the pin number 29. So all these things you can explore yourself a little bit. Okay, and then let me come. You will ask me that, okay, two buttons are there, two LEDs are there, but where is the third LED? So for that we come to PWM. In PWM, you see that one LED has been configured in the PWM mode, and in PWM mode, this is the particular pin, that is P01, pin number 9, and there is a timer, that is timer 3, which has been considered. You can take any of them, but any means the system will automatically configure as timer 3. And in this particular timer 3 application, will create the duty cycle that is required for the PWM functioning. Okay, so just remember, in the GPIO these two have come. So if you need to create more GPIOs, just click on this plus button. You can see that one more GPIO has been created, which has been by default given in the name as config underscore GPIO underscore 2. If you want to change the name, you can change the name here. If you want to use any other hardware, you can use, since we don't have any other buttons, so we cannot help it, but if you want, you can, if you have, you can use it. Okay, then mode you can select as input and output. So all these things you can just explore yourself. Okay, right now I will not mess around with this because it's a very critical file. So that particular config button 0 I'm passing over here. Handle button callback, it's basically a callback function that will be immediately passed on whenever the button whenever a button event is generated, and the event will be found from here. Okay, so now you can understand that from the button open function, we pass on the button, we register the callback that is going to be called back whenever any event triggers, and that trigger will be passed on to the memory area of, I would say, of this array, button handle array position 0. So this is how more or less the button handling is being done. I understand maybe it is a bit difficult to understand for you, all those who have not worked on RTOS. If you have worked on RTOS, then it will be quite okay for you. So like button config button 1 also, it is being done in the same way. Okay, so these it's a well commented code, so you can also understand yourself. If in case any one of these two open button functionalities goes wrong, you will have this printed through your display UART handle. Okay, now let us come to the LED. So similarly, as button parameters were initialized, the LED parameters will also be initialized. We have declared the LED params over here. Okay, so the one is the blink period, the brightness, the set state, That is whether you want to set it as blink, or you want to set it as normal, just turn it on. If you are using it in the PWM, what will be the PWM period? So all these things are there in the LED params. You can just go through all these kind of details and let me know if you don't understand. So here we have just declared that particular structure, and in this particular line we are allocating memory to it. So once we allocate the memory to it, and we declared the particular structure variable, the next thing we do is, like we had opened the button to get the handle for the event, here also we are doing LED open, but here there is no callback that is required, because button has separate events that can be fired, so those events will be handled inside the callback. But here in the LED, like for LED, for the LED 0 and 1, it's just two events, that is not two events, rather I would say that for LED it's like either it will be turned on or it will be turned off. So we just acquire the LED handle from the parameters over here, and then if you go a bit down, you can see that if the LED count is greater than 2, which in our case is true, then what will happen is they have created another PWM section, wherein they have created another LED open. I would say they have created another instance of the LED open function, and they have passed on the LED parameters, and here we get the handle for the pulsating or the blinking LED, which is happening in the middle. So as we see that LED params dot set state is equal to LED state on, so the LED state will always be on in the kind of in the case of the middle LED, that is a pulsating LED, and then we pass the handle to it, and once we successfully pass the handle to it, then here you can see how the duty cycle is being calculated. So once the duty cycle increments from 0 to 100, and then it slowly, once it increments and then it slowly decrements, and that will help generate the PWM, which is like a heartbeat, or they call it heartbeat, but it's like a pulsating functionality, which is done for config LED2. So that is a PWM. So that is controlled by a timer, and that is automatically done inside. Okay, and after everything is done properly, you can see that the system goes into a sleep mode, or not the system, rather I would say this particular section of the function will, it'll go around in a while loop. So once it goes around in a while loop, this particular thread will not be exited. So whenever all these things are done, and do event logs will basically print which event has been triggered from the button. After that, the system will go to 50 milliseconds of sleep. Just remember that there are two sleep functions. One is normal sleep and the other is usleep. Now usually Linux systems, I think they do not allow I think somewhere around delays lesser than 1 millisecond. So here I think it is Linux system doesn't allow delays lesser than, I think, 1000 milliseconds, but here you can give delays in terms of microseconds. So this particular while loop will go into sleep mode, or rather this particular thread will be in sleep mode for 50 milliseconds, and after that this while loop will again go around. You can just go through this while loop and see how the pulsating function is being done, because it is not something that is very critical. LED set on is basically called here to control the pulsating, and we are passing the handle, the LED handle. Since we are passing the config LED2 handle, so LED set on function knows that which particular LED it has to access, and the duty cycle is passed over here. So this calculation, I think you can do it yourself. Rather, we can just go directly to the callback function, handle button callback. So in the handle button callback, uh, I would just go through a very basic overview. What is happening is whenever you press the button, three type of events can happen. One is you can just click it and release it. The other is you can double click it and double release it, and the other is you can keep it long pressed. So whatever button you are accessing, that handle will be passed on in this callback, and whatever event is generating, that will be passed on over here. So according to the events and the handle, different kind of actions will be taken. Like for example, once the button is pressed, you will see that this particular structure variable will be incremented, that is bstat pressed. Okay, whenever it is released, again the released variable will be incremented. So from the pressed and released, you can calculate the last press duration. Okay, and there are also a condition that is called EV clicked. So basically what they are doing is, in this, or rather what we are doing over in this particular function is, we are calculating the last press duration, because according to the last press duration, the LED blinking will be controlled. Okay, and after we understand that what duration has been done, okay, what duration has been done for a particular button handle, the ring buffer is filled with that particular event. Okay, so we understand, like once you understand that which event has actually generated the callback, so that event can be inserted into the ring buffer. So after it is inserted into the ring buffer, the LED stayed blinking. So I told you, in the LED we do not have any registered callbacks. The reason is this, because the LED functionality is directly controlled inside the button callback. So if the state is blinking, you can just do a stop blink, otherwise you toggle the LED. So if it is a long press, then you have this particular processing, it will, for a long press, it will keep on blinking the LED forever. Okay, and for a double press, you can see that the LED will start blinking. It will blink, I think, 3 times, and then it will go to off state. So this is basically a very brief overview of what is happening. And do even logs is basically giving you the logs on the UART using the display handle. So what I wanted to tell you here is that once you just go through this particular code, try to understand at a very basic level that what is happening. You can insert breakpoints like this. If you want to make a breakpoint over here, you can insert it like this and try to see that what are the values inside the various register. So right now what I will do is, I will compile this code and I will download it for debugging. Do remember that if you are compiling and debugging for the first time, it will take a good amount of time, so please be patient. Don't try to click here and there, because CCS is sometimes it is vulnerable. Hey, so here we have the code downloaded. Great. So now what we can do is, it's saying, the console says the target has been reset and initialization is, memory map initialization is complete. That's great. So now what we will do is, now I can just open my terminal and clear out all the data that I have received, and let me just share my screen like this. I don't have a very big window or a monitor right now, so I'll try to manage with this only. So you see, the function is starting from main, right? So what it will do, it will come here to this particular line, okay, and it will jump to main thread. So what I will do is, I'll go to main thread and I will put a breakpoint right out here. A breakpoint is inserted by taking the mouse to line number 189 and just double clicking it. Double left click will insert the breakpoint. So the resume, or this green colored resume button, can be used to start the debugging, or you can just press F8. Okay, so you see that it has come over here. Now what I want you to see is, I told you about Gpio Init, right? So once the Gpio Init is done, I will do another breakpoint. Okay, so what I will do is in the Gpio Init part, what we will do is we will go to the registers over here. You know, this is a beautiful thing of CCS. It's like you can see all the registers very clearly and even the memory area. So what I will do, I will go to the GPIO section, and we know that which pin we have used. So right now it will say that it is unable to use the data, but you can just go to this particular section, and then hey, so here you see that GPIO A1, these are the the registers that I told you, and here you have all the registers, you know, that comes under GPIO. And you don't have to, you know, bother about all the details that is happening into it, or what are the detailed values that has been placed into it. Just look into it that these two GPIOs has been initialized, because the others will tell you error unable to read, which means that clock gating hasn't been enabled, and maybe that is why it is not able to access the GPIO. So for GPIO A1 and GPIO A2 you will be able to access the data, but for GPIO 0 and 3 it will be unable to read. Okay, so we can just, you know, make a basic assumption that GPIO A1, and because the direction of, I told you that GPIO DIR register will basically help you, you know, decide the direction of the pins. So let me just quickly open the data sheet I was showing in the previous video. Okay, so I have come to this particular register. You can see that DIR, that is GPIO A1 DIR, has a value of A. So if I go into the technical data sheet, I will see that GPIO data register, that is this one, the last 8 bits basically signifies that, you know, which memory location I need to access in order to output my data. So over there the data that has been written is 00001010, because 0A is that basically when we expand it to a binary. So basically bit number 3 and bit number 1 has been set. Okay, so bit number 3 and bit number 1 has been set. So that will give you an idea. Also for I think even for GPIO A2. Okay, so only for A1 we have. Okay, now let me just go back to CCS edit. Okay, let me tell you one more thing. In the top right corner you can see CCS debug and CCS edit. Okay, if you want to go back to edit mode, and if you want to see any file even during a debug session, you can just click on the CCS edit. So in CCS edit, let me open the sysconfig once again, and in GPIO I can see that button 0, GPIO 0, I can see to which pin it was connected, P04. Okay, so that was basically pin number 3. Okay, so what I will do is I will open the data sheet. Okay, so what I was telling is for these two GPIOs we can see that one is GPIO number 3. Okay, this is GPIO 3, and for this one, this button, it has been taken as GPIO 11. And for LEDs, if we see that for LEDs also, we can see that it's GPIO number 29, and GPIO number 29 and GPIO number 10. Now let us go to this particular dataset section. So GPIO number 10, as we can see here, okay, GPIO number 10 was 1 and the other one was GPIO number 3. Oh, I'm sorry. The other one was GPIO number 29. So GPIO number 29 you can search out here. Okay, so let me just use any one example. Let me use this example, GPIO number 10, which was LED 0. Now LED 0, LED 1, sorry, LED 1 is GPIO number 10. So if you open the datasheet, we see that GPIO config 10 is here, right? So this is the GPIO here, GPIO 10. So this is the one that we have used for this particular LED, that is the green LED. So now if you see that for this particular GPIO, what is the register address? It is 4402E0C8. Okay, 4402E0C8. So now let us come back to this technical data sheet. I told you that all the addresses starts with 4. So 4402 means that from this base address you have to add. We are accessing GPIO dir register, as we can see. If we go to debug mode, we are seeing the GPIO dir register. So it's like it's 4000.4000, for example, or for A1 it is 400.50000. Along with that you add 400 hex for your GPIO register. So you have to add this particular value to the offset, and after that you have to compare with the data that we are sending to the output port. So it's like this, that the comparison is done. I'm sure it's not very clear to you. I mean, I will try to clear it up in a separate video session, because this is a bit more complex into the ARM architecture. So right now just try to understand that 2 pins has been activated as output pins, because A is 1010 and those ones are basically the pins that has been considered in the direction register. Okay, so once again, just remember that 1010 means bit number 3 has been considered as an output, bit number 1 has been considered as an output, and all the rest as of now has been kept as an input. Okay, so button init, I will just stop once again over here, and you see if you see any kind of changes in the data. I'll just leave it up to you to study if there is any kind of change. If you see, okay, this is the IEV register, interrupt enable register. So these kind of study, if you want to go into such depth, you are most welcome to do, but let me tell you, it will take a lot of time. And if you are really bothered about going into driver development, then it's important. Otherwise, for application layer, I think it's not important. So let us just run our code and see what happens. So here our code is running, and you can see that these two LEDs, these red and green LEDs, will shine up to show that the debugger mode is on. And now if I press any button, you see that the red LED is on. And if I press this button once again, the red LED is off. If I press this button, the green LED is on. And if I again press this button, the green LED is off. If I double press, you will see it blinks 3 times and goes off. And if I long press, then the LED, as long as I'll keep it hold, the LED will keep on blinking. Now what I wanted to make you understand is, it is because of the RTOS that even if I place both the systems as long press hold, both the LEDs will keep on blinking, and the middle one will also keep on pulsating. It is because we are triggering multiple events in the callback functions, and they are being managed by the RTOS scheduler. So that is it. You can just do some more in-depth study into it, and once you are fine with the the debugging, you can put multiple breakpoints and see which condition or which event is being triggered. So once you are done with it, you can just click on this terminate button. But let me remind you one thing, that since this code has been not downloaded on the flash, if you reset the board, it will again go back to the original code that is already residing in the XIP flash if you have the SF version. So it will not be this particular code that will be functioning. So don't think that your code has got destroyed or something like that. It is just because your code is running from the internal memory of the microcontroller or the CC3220SF. That's why it is happening like this. If you want to download this code permanently, then there is another process using the UniFlash that I will separately discuss in a video. But as of now, once you terminate this session and you reset the board, your code will be removed. Okay, so I think that is enough for this particular session. You can also see all the data that has come on my hyperterminal or HTerm. Here you can see that whenever I have pressed a button, if I press it once again, you can have a button click, a double click, and a long press. Okay, so this is it. Thank you very much. Next time, in my next video, I will come up with the ADC. Thank you. If you have any questions, do get back to me.